Good morning to all of you, and welcome to this invited talk. It is a pleasure for us to welcome here at the Technical University of Crete, Professor Stanisław Wrona from the Silesian University of Technology in Poland, in Gliwice, Poland, which we visited a year ago. So around this time, May last year, we were there. Professor Wrona is visiting us here at the Technical University of Crete in the context of faculty exchange visits within the European University, EURECA-PRO. And this is the first of these visits, and we hope to have more in the future. So we can't wait to hear about your topic today. But before that, let me say a few words about Professor Wrona. He received his PhD and DSc degrees, both in automation, electronic and electrical engineering, both from Silesian University of Technology in Poland in 2016 and 2022, respectively. So you're a pretty new PhD graduate. And so currently you are an associate professor, as I read, at the Department of Measurements and Control Systems. And you have a lot of experience in control methods. Professor Wrona has worked very closely with Professor Marek Pawelczyk, whom we know very well. And it is actually very nice that through this connection we have you here today. The two of them have published a monograph titled Noise Controlling Casings, which is exactly the topic of today's talks. And so without saying anything more, we'll give the floor to Professor Wrona. And after the presentation, I guess we will have time for a few questions and discussion on the topic. So once again, welcome to the Technical University of Crete. The floor is yours.
Thank you very much, thank you, Professor Wrona, for the introduction, and thank you for attending this seminar. It's my pleasure to be here. Before we get to the main topic of this seminar, the noise controlling casing, please allow me to give a few words of introduction about my university, Silesian University of Technology. So, Silesian University of Technology is located in the south of Poland. It's the only technical university in metropolis, in Poland, which has a population of more than 2 million. It has also, the region has special economic zone with more than 100,000 jobs and more than 200,000 jobs related, and 500,000 of companies in the region. So it's pretty industrialized region of Poland. There are also 5 research institutes of the Polish Academy of Sciences, and all this environment, which is visible here, marked on the map. You can see it clearly, distinguished from the rest of the country. It led to advances in many different technologies, in ICT, in the chemical sector, automotive, aviation, and the biomedical sector as well. The university itself has a modern infrastructure and campus located very near to the city center. It has both newly built buildings, modern laboratories, and also some more historical sites as well, because it was founded in 1945. So it has already quite a bit of history. SUT, as I will call in abbreviation the university, was selected as one of the 10 research universities in Poland, which was an important distinction because it also comes with extra funding from research for extending the infrastructure. So it was distinguished as one of the top 10 research universities in Poland. SUT is also part of the European University EURECA-PRO, which also allowed us to organize this talk, which is very much my pleasure. Of course, within this university, Technical University of Crete is also important partner. So we are part of this initiative. Moreover, Katowice, which is the center of the metropolis which the SUT is located in, will be the European City of Science in 2024, in the next year, together with other universities located in the metropolis, together with University of Silesia, Medical University, and other academic centers as well. So the whole region of Silesia will organize this event in the next year. We have 13 faculties within the university, and also the one institute in physics. So we cover whole variety of different technical disciplines within our university, and also some extra disciplines related to organization, management, and business as well. We have distinguished 6 priority research areas: computational oncology and personalized medicine, artificial intelligence and data processing, materials of the future, smart cities and future mobility, process automation and industry 4.0, and climate and environment protection and modern energy. So these are the 6 main areas which the university is focusing on, but actually all these areas are pretty wide, and it covers a wide array of problems. And what also gives, I think, a good idea of the scale of the university is putting SUT in numbers. So 16,000 is the number of students at the university, both undergraduate and both in bachelor and master courses. We have more than 800 PhD students, more than 2,100 graduates, 12 research scientific disciplines, 6 priority areas. As I said, the academic staff is more than 1,600, 130 full professors, and more than 3,000 employees. So that will put more or less in numbers the scale of the university. Here are the key objectives for development of the SUT, which is obviously the quality of research, excellence based career development, modern education, collaboration with industry, and internationalization, where the European University EURECA-PRO also helps a lot. There are a lot of investment in excellence. So here we have some information about the budget within the period mentioned here, which is divided into these 5 areas. And there's also a societal and economic impact of the university. There are mutual involvement in strategy development, share of the expertise with the commercial companies, with the environment in the region, the infrastructure share, study programs motivated by the needs of the study program is adapted in different areas, different faculties. There are joint R&D centers, joint projects, and rapid response to requests. We follow the modern education principle. We implement problem and project-based learning. Students like it very much. I saw also that at the TUC, you also follow the same principles. I just saw some of the projects, so I believe we have the same experience, how it motivates the students. We also organize dual studies, flexible study track, and PhD school jointly with scientific and research institutes. And there are more than 180 students research clubs. Some of them that we can mention here is Silesian Green Power, which build cars that aims for low energy consumption, both electrical and combustion cars for different competitions. Electra, Silesia Automotive, High Flyers, and Smart Power. And we also have a business school which allows to make the MBM studies as well. We also are engaged in cooperation with business environments. So here I mentioned some projects that we're involved in. And the cooperation with business environment also, what follows from it is we have the Center for Incubation and Technology Transfer, which allows the spin-off companies. It engender the start and allows them to develop in the first stage of development. It helps the scientists establish also industry partnerships. So this would be a brief introduction of the university, and now I would like to swap to the next topic, which is the main topic for today's meeting, which is the noise controlling casings. Okay, so first to introduce the topic of noise control, I would like to mention that noise is currently named as one of the most significant threats for humans' well-being. What we mean by noise is both the noise that annoys us in the home environment. A washing machine can be annoying, but also in the industry, it can be a much higher level, which could lead to hearing damage and other health issues. So it's named as one of the most important trends also by the European Acoustic Association and so on. The commonly used noise reduction methods are often ineffective, especially against low frequency noise. We know the principle that the barriers, the passive barriers, have to be thicker if we want to treat low frequencies. So there's always some limit of the thickness of the barrier that we can apply. Sometimes we even cannot apply any barriers due to heat insulation. If the device itself will produce heat, it needs to be ventilated. So it's impossible to cover it from every side with thick sound absorbing materials. So often we are not allowed to use the passive sound absorbing materials to cover all the noise problems, and such application motivates the scientists to look for new ways to reduce noise. And one of these ways is to use active methods, which uses actuators like speakers and also vibration actuators like exciters to control the environment in order to reduce noise. And among active methods, we have two main approaches for the noise control. One of them is active noise control, which we can call also like a classical approach, when we use loudspeakers to generate so-called anti-noise. So if we have a source of noise in the environment, we can put a microphone near the source of noise, through which we would call the reference microphone. It would give us information about the noise, and with the loudspeaker, we'll use it to control the environment and generate anti-noise to use the destructive interference and create zones of quiet. And depending on the frequency of the noise, if the frequency is higher, the zones will be smaller. At some point, it would be infeasible to make very small zones, like of few centimeters. So there is a limit for which these methods are useful, feasible, like a couple hundred hertz, in order to make a zone of quiet of half a meter or meter in 1 meter in diameter. Moreover, with this classical approach, the ANC, in 3D dimensional spaces, it's difficult to make and maintain these zones of quiet. If there would be changes in the noise of source, if the noise source would move, it would be difficult to make to maintain the zone of quiet in one place. It also could be difficult to add many loudspeakers in order to control the environment. Moreover, with the ANC approach, the classical approach, there are issues with noise enhancement. So we create a zone of quiet in one place, but we enhance the noise in other places. So if there is only one recipient in the environment, in the room, that's okay. But if there are many of them, we either have to choose between them or try to find a trade-off, which would limit the performance. So there are many difficulties with this approach. But we can apply a different approach called ASAC, the Active Structural Acoustic Control, where we create active barriers which do not allow the noise to pass through the barrier. And the barrier can be just a plate, it can be a plain barrier, which would separate like one room from the other and reduce noise. A window can be considered such a plain barrier, but actually this approach can be used also for the whole casings, which would enclose the source of noise inside. And then I believe it would be even more feasible because we can pick a source of the dominating source of noise. We can put it in a noise controlling casing and reduce the noise actively without applying any heat insulation and allowing effectively to treat the low frequencies. So this is the approach that we follow mainly in our research, and this research that I will present here is the research that I'm involved in, but it's also the result of the whole team led by Professor Marek Pawełczyk, which was already mentioned by Professor Ilior. Moreover, I would like also to mention that the active methods is something that we started our adventure with noise controlling earlier, but the active methods themselves can be supported also by other methods distinguished by the energy point of view, how they use the energy and where the energy comes from. So with active methods, we need to introduce the energy to the system. And this leads also to some difficulties, like we need to make sure that the system is stable, because if we introduce new energy to the system, we need to take care about the convergence of the control system in order to make it stable and to reduce noise. But the performance provided by active methods offers highest possible noise reduction. It can, in many applications, exceed 20 decibels. So here we have one of our applications, which is a washing machine. This approach obviously does not limit to home appliances, but in case of home appliances, we've found industrial partners which are interested in mass production of such methods, because in case of such devices, the generated noise levels is an important factor for buying a certain product. So the companies were interested in it, and we applied the active methods for example, this washing machine. So in case of the application of active methods to such device casing, we control vibrations of the casing in such a way to reduce the sound radiation to the surrounding environment. And what I think can be surprising is that when this system is operating and when this noise is reduced, it doesn't mean that the vibration have to be reduced. The vibration distribution is altered, it's different, but the amplitude can be even higher. For the first time when I noticed it, I thought that there was some mistake, but we repeated these experiments many times, and most often the amplitude of vibration is higher, but the distribution is different, making the noise to be radiated, the noise radiation is reduced. So the distribution makes the air to flow at the surface of the casing, and it's not like pushed forward, and it's not effectively emitting, radiating the noise. So this system requires a control system, some CPU microprocessors in order to operate, but the performance can be highest, especially if the noise is periodic, if we can somehow predict what would be the noise. So whenever there are tonal components, periodic components of the noise, it can be treated very efficiently with this approach. Another approach that we used in order to either support the active methods or use as separate solution are semi-active methods. In this case, we try to alter the properties of the barrier, because each barrier made of metal sheets like here, which the casings are made of, will have to have some natural frequencies at which the noise reduction will be poorer. So we thought that if we can manipulate in real time these natural frequencies, then we can try to adapt to the current noise spectrum, assuming that it's not broadband and covering the whole spectrum. If there are only some single frequency or some tonal frequencies of the noise, then we can adapt the properties of the barrier. So we've tried different actuators in order to modify these properties. So in this photograph, we can see a double panel barrier with semi-active links between them, which are connected to both plates. And with a binary control signal, we can either couple these two plates together at this particular location of any of these links, or decouple. And in such a way, we strongly modify the natural frequencies of the whole barrier, and we can modify the transmission loss of the barrier, adapting it in the real time to the noise spectrum. And these links are stable, so it means that they do bistable, so they don't need any energy. Once they are switched, they don't need any energy to support. So we only need energy to switch the state of any of these links. Otherwise, they are either coupled or decoupled without any extra energy involved. And finally, the passive methods, which might seem pretty simple, but such modification to our barrier, if we know a priori what will be the noise spectrum, can also help us adapt the properties of any barrier. What we've done in our research is, by modeling the barrier, we can predict where to add a particular mass in order also to move the frequencies, but not in semi-active way, but in passive way. So by adding appropriate mass at specific location, which follows from the optimization algorithm and the model of the barrier, we can shape the frequency characteristic of the barrier and enhance the transmission loss at any of the frequency band that we would like, depending on the noise spectrum. So if we know what will be the noise spectrum, we can benefit from these both strategies. The first one, active approach, is most comprehensive, obviously, but it's also most energy consuming and the cost is highest. But if you would like to reduce the energy consumption, in case of semi-active, use the energy only to switch the states, or in case of passive methods, without any energy, we can also achieve, I believe, pretty attractive noise reduction levels, reaching even 10 decibels for real devices like a compressor and so on, when we know what should be the frequencies and when the frequencies are tonal. And finally, the fourth approach would be to use more than one of these approaches together. We've done a research with one of the semi-active components in order to change the properties of the barrier together with the actuator. So the semi-active component, its purpose was to adapt the properties of the barrier in order to enhance the controllability of this actuator, making this actuator more efficient. So I will show us specific results in the second part of this lecture, but I believe that this introduction gives an overview of the methods that can be used to these noise control issues. So the purpose of this seminar is to discuss the modeling, optimization, and control methods in noise reduction systems. And as a part of which is devoted to control all of these three categories, some examples of all of these three categories, active, semi-active, and passive, will be shown. And this presentation have a review character showing different solutions, but it contains also a number of practical remarks that I believe can be interesting to researchers and practitioners. Okay. In this section of modeling, I will briefly explain what models we've used to model the barrier, but we don't get into the equation because I believe it's not necessary in this presentation. I will just show what are the model used for and what are the benefits of using this model. So first of all, what is the purpose? The modeling of vibroacoustic systems is crucial for their optimization. If we have a proper accurate model, then we can optimize many of the barrier parameters, making it much more efficient. So the optimization can lead directly to noise reduction by finding optimal configuration of passive elements. As I just showed, that putting a mass even on a magnet can drastically change the characteristic of the barrier, and therefore it can enhance the noise reduction. On the other hand, the optimization can find favorable locations of actuators and sensors for the active noise control system, and therefore it can also benefit the noise reduction. And the mathematical modeling was focused on barriers that separate the noise source from the receiver, either for plain barriers or whole casings, whole boxes. So firstly, the modeling was developed for plates, rectangular plates. The model described the vibrations of plates with elastic boundary conditions, with concentrated masses and stiffness used to passively modify the properties of the barrier. The model allowed to predict natural frequencies and vibration modes, which is also important because the vibration modes, the distribution of the vibration, is crucial for calculating the radiation efficiency, noise radiation. And knowing that, we can also benefit, which I will show in the next slide. The practical effectiveness of this approach of optimizing these frequency characteristics are shown in the later part devoted to control. So the two capabilities of this method of shaping the frequency characteristics of the barrier were revealed after extension of the model with the phenomenon of acoustic radiation. So when we was able to modify, to shift the natural frequencies, this was beneficial, but actually it was even more practical when we could model the acoustic radiation and modify the mode shapes, the vibration distribution in such a way to reduce the radiation efficiency. So the purpose of the acoustic barrier, we stated that is to reduce noise, and the vibration amplitude is actually not important. So we allowed certain modes to vibrate as long as they're not really radiate any important noise component. So it became possible to shape the distribution of vibrations in such a way as to reduce the coupling with the acoustic medium. And what's interesting, this effect, this phenomenon, was doubly beneficial if the noise source stimulated the barrier purely acoustically, because if this barrier was excited by a sound wave, it was more difficult for the sound wave to excite the barrier for these particular frequencies, as well as this barrier, when it was already excited, to pass it further with the radiation to the environment where the recipient is. So it was doubly beneficial in such a cases, but also beneficial if the barrier was stimulated vibrationally, structurally. We've used the model also to position to optimize the location of sensors and actuators. What we noticed that less than half of in case of optimization of actuators, maybe I will add one more introduction, that initially we tried to optimize the actuators in such a way to control every mode of a casing or a barrier, but actually it was not really optimal approach, because what we noticed is that only half or less than a half of the modes are really contributing to sound transmission or radiation. So in case of optimizing the sensors and actuators and being able to model and predict the acoustic radiation, we could focus with the optimization only on those modes that contribute to the noise radiation and noise transmission. And this led to significant improvement in energy efficiency only for these acoustically significant modes. In case of, to give a tangible example, when optimizing 3 actuators on a plate, by allowing to include the acoustic radiation in the model and focusing on the acoustically significant mode, it gave the same controllability boost as adding an extra actuator. So we allowed to not be able to control insignificant modes. We focus on the significant modes, and this increased the controllability. And by controllability, I mean the energy that we need to input in order to control these modes. So the controllability was much greater for these acoustically significant modes. In case of double panel barriers, we've molded such structures with the links that I already mentioned. And this new kind of semi-active component was proposed, which couple or decouple the barriers. We propose this link, which allows to adapt the properties of the barriers. Later in a few slides, I will show what was the performance of this, of these links. And finally, finishing the part related to modeling, we've also, together with the Universitat Politécnica de Valencia, we also implemented this approach for rooms in order to optimize the locations of microphones and speakers in order to generate the zones of quiet. This approach is the classical ANC approach that I mentioned in the beginning. So in case you would like to optimize the shape and distribution of these zones of quiet, we can also use this similar optimization approach. Although this research that we are doing focuses on the ASAC approach, structural noise reduction, it can be also successfully applied to this classical ANC research. Okay, now dealing with the optimization, as I said, it can be used either directly to modify the properties of the plate. So by adding stiffeners and masses to the plate, we can modify the frequency characteristic, as we can see here, from the original characteristic marked with the dashed gray line to the black solid line. So if the cost function was to reduce the acoustic response of the plate and reduce the acoustic radiation with these components, we can see here that these 2 dominating resonances were reduced by approximately 10 decibels in the considered frequency range, which was up to 300 Hertz. So just by adding passive components, we can reduce the acoustic response and therefore increase the transmission loss for such barriers at these resonances by approximately 10 decibels. So I believe it's pretty beneficial, assuming that the noise source can excite these particular frequencies. If you want to make a universal barrier for the whole frequency range, these modifications can allow the barrier to be more efficient noise barrier. In case of structural response and vibration, not much changed, but in case of acoustic response, the difference is clearly visible. Okay, and now the final part, the control results. So firstly, I will show the results for active casing method, and then I will follow with the results obtained for semi-active solutions and mention the hybrid solution. What we call the passive control because there's no really a control system. What we call by passive control is this modification shown here. So we can say that this was introduced here, and now we focus on active and semi-active control. So starting with active control, here we have an example of the results of noise reduction for a washing machine during the spinning phase. And with the red color, we can see the frequency characteristics when the control is turned off, and with the blue color when the active control is turned on. So as we can see, basically all of the frequency components up to approximately 300 Hertz are strongly reduced, often by more than 10 decibels. And these frequencies are harmonic frequencies of the velocity, rotational velocity of the drum. And this low frequency range is clearly sensible by humans. So this reduction in the low frequency noise is also most difficult to address with passive methods. So this is what we managed to obtain with applying the active casing approach. Here the results are obtained at the aero microphones, and here which are around the casing, and these are the results obtained for the monitoring microphones, which were placed in the greater distance from the casing, somewhere in different places in the room. So we can also see that we can obtain strong reduction up to approximately 300 Hertz. We're trying to push this limit forward, maybe to 500 Hertz, but we still need to fill the gap between the active control band where it is efficient, and the band where some passive thin subabsorbic materials like a felt, layer of felt, is also efficient, which starts from approximately 1 kilohertz. So this frequency bound between approximately 3, maybe 500 hertz up to 1 kilohertz, it still needs to be treated. But with this approach, we can very efficiently reduce the lowest frequencies, which are also most difficult to treat with passive methods. Now passing to the semi-active control approach. Now I will show the results that can be obtained for these passive links, and this research was done together with Hong Kong Technical University with Professor Li Cheng. And here we can see, firstly, maybe I will draw your attention to the frequency characteristic marked with the red color of a typical double panel barrier. In case of double panel barriers, they offer pretty good noise reduction for higher frequencies, but there is always an issue with two first resonances called mass resonance, which is always present for any double panel barrier. So there is plenty of different approaches, solutions for treating these resonances, these mass resonances, which occur in any double panel barriers. Even double glazed windows have the same issues, that we can hear that some frequencies are so easily passing through these windows. And the solution that we propose, how to deal with these two peaks, where we can see that the attenuation is weak, because if the characteristic is lower, it means that the attenuation is greater. So we need to treat these two peaks. And our approach here assumed that the noise would not be broadband, that it would be rather narrowband or tonal. And in such application, we can modify this characteristic and move these resonances by changing the state of these bistable links. And by doing that, we can generate, in this case, we only used one link located at the center between the panels, and only with one link, which allowed us to switch between just two states. It allowed us to switch between two different characteristics, and the minimum of these two characteristics is marked here with this black line. So we can see that we can always find a solution without these resonances. So we can get rid of these resonances as long as the noise source is narrowband or tonal. And the benefit from this approach can exceed even 15 decibels. So I also believe that it is a quite attractive solution, especially that these double panel barriers are commonly met in many different applications, many different environments. Like even the airplane fuselage also is double panel structures. In buildings, we have double panel walls between rooms and so on. So we can adapt this solution to many different applications. After this research, we also wanted to develop a semi-active actuator dedicated to single panels, because these links proved to be efficient for double panels. But how to modify to such extent the properties of a single panel, where we assume that we do not want to find a support, we don't want any supporting structure in order to connect it to something. We wanted to put an actuator on a single panel without any extra mechanical support. So we designed our own actuators with movable mass, which modifies the mass moment of inertia. And therefore, it would modify the model mass of the vibrating modes. So if we put this actuator on a plate surface which rotates, let's say that it would be another line. So there would be no movement, no transition, change of the position, but just the rotation. If we place at such another line this actuator, by moving the mass, we would change the model mass, because if it would be lower, closer to the surface, it would be easier to vibrate, to rotate this actuator. If it would be moved by this motor and a screw here, if the mass would be moved further from the surface of the plate, and then the moment of inertia would be greater, and respectively the model mass of this particular mode would be also greater, and the frequency of this mode would be altered. So with this approach, we don't need any external support, and we can still shift some of the modes when we do not put this actuator on a antinode. If it's somewhere in the proximity of the nodal lines, then this actuator would be efficient for these particular modes. And dividing this range of the position of this mass into 10 different positions, for an exemplary plate, we can obtain 10 different characteristics that we can choose from, ranging from 10 millimeters to 100 millimeters from the plate surface. And this whole family, this set of characteristics are marked here with this light gray. With the dashed red color, we can see the original characteristic of the barrier of the plate without any actuators, just for comparison. And with the black line, we can see the optimal solution, which is basically the minimum of all of these 10 frequencies. So assuming that we will have a noise of a single tone, we can always pick the most beneficial out of these 10 frequencies, which means that the most beneficial position of this mass, and therefore avoid excitation of any of these modes. So in case of narrowband noise, it allows to eliminate basically all of these resonance peaks. So it can be used for both single panels, but actually as well it can be attached to one of the plates of the double panel barrier. And finally, we also applied these two components together. Here, I still don't have the frequency characteristics to show you, but I will explain what the concept is. So in such a case, when we employ both of these actuators, we can distinguish two operating modes. The only semi-active mode, which works, as I previously explained, just by moving this mass and choosing the most beneficial frequency characteristic, and also active mode with semi-active support. This means that we will adjust the location of this mass in such a way to most benefit the controllability of this actuator. Normally, we would not be able to control all of the modes, or at least not even initial 10 modes of the plate with single actuator. Why? Because if we add the actuator at any location of the plate, these modes rearrange in such a way that the second or third mode of this plate would always have a nodal line going through this extra concentrated mass. It always happens like that. So with single actuators, normally it would be not possible to control the initial 6 or initial 10 frequencies. Some of them would be always uncontrollable, and therefore the noise would pass through as to a passive barrier. But with adding this semi-active component, we can modify this frequency characteristic in such a way that even with single actuator, we can always control each of the modes. Obviously, these two locations have to be optimized, because accidental location will not guarantee that we could control all of them. But we showed that with only one actuator and one semi-active element, semi-active component, we can pick such two locations that allow to control initial, I believe it was 10 or 12 modes. So to conclude this talk, the noise reduction methods can be applied to device casings, and they have a high potential to support or replace classic sound absorbing materials, which have their disadvantages that I mentioned earlier. And depending on the availability of energy, external energy, it's possible to choose between active solutions, semi-active solutions, or completely passive ones. And in the low frequency band, active methods can offer more than 10 decibels of reduction, in some application even more than 20 decibels. And assuming stationary or non-stationary but narrow band noise, the presented passive and semi-active solutions can also offer more than 10 decibels of reduction. Thank you very much for your attention.
Well, thank you very much, Professor Wrona. The topic is very interesting, and as we speak, actually, in this room, we have a permanent source of noise, which you may help us to reduce at some point anyway. So time for questions. We have the wireless microphone. And okay.
Thank you, Professor, for your real, very interesting presentation. You saw us in your presentation that these materials or these methods, both active and semi-active, are very efficient in absorbing noise at low frequencies.
Yes.
Maybe up to 10 decibels. Okay. What is the reduction in higher frequency, for example, in the range of 1,000 to 4,000, which is the acoustic range? What is the range of attenuation we expect in this spectrum?
Okay, in this spectrum, I believe that both the active methods that I showed and semi-active would be very difficult to apply and to achieve satisfying performance. In case of active methods, it would require very strong computational power. The system would have to work at much higher frequencies that usually it does, and also there are limits that comes from the also like mechanical point of view and the distribution of the modes. So I'm not aware of any of the active control methods that would successfully operate and implement the active structural acoustic control for such high frequencies. Mm-hmm. So it would be, I believe, very difficult. Also, it would be difficult to monitor the environment around with such short sound wave to allow to provide the global noise reduction. In case of semi-active control, then there will be another issue, because when the frequencies goes higher, the density of the resonances becomes also higher. They are denser, and it would be difficult to control each resonance one by one. So, also the accuracy of the model, at least those that we've used, also drops for the higher frequencies. So it will be difficult to precisely model and predict what will be the resonances after specific modification. So I believe that for such frequencies, we should rather use passive solutions, either classical sound absorbing materials or metamaterials, if possible.
Okay, thank you very much.
Thank you.
Thank you for a very interesting presentation and for this topic that I think is very important. We don't realize how important it is for health and well-being, as you mentioned. I was wondering about the vibration increase that you realized during your experiments, the initial experiments, and if this vibration increase is less than the ones specified for this kind of machines, because if the vibration is increased, then sometimes goes beyond the limits of operation of the specific specific machines. And the other question is, I would like to have your comment regarding the energy required for these operations, how you manage to cover the energy requirements for this. These are my two questions. Thank you.
Okay, thank you. I believe it's a very good question because the energy consumption is an important issue. Also, from the point of view of actuators that we can use, the inertial actuators, in order to be small enough to not load too much the casing, the energy output is also limited. We started with actuators of only 5 watts, which was really not enough for many applications. Even the noise source was too strong, we were not allowed to generate enough power. Now we have better actuators of approximately 40 watts per actuator, so it's better, but still we need to keep in mind that the output is limited and we don't want to put too much actuators because it would increase the cost and practically it would be impossible. So we keep this in mind, but when we focusing not on vibration reduction, but on noise reduction, in fact, we don't need to counteract the vibrations. We don't need to be stronger than the noise source. We only need to alter it. And then we only need a fraction of the energy, to use only fraction of the energy of the noise source. It's like pushing with a finger, just a specific point, and rest of the vibration rearranged. So we only just slightly push here and there, and then it allows us to modify beneficially the distribution. So the energy consumption with this approach is much, much lower than if you would like to counteract the vibration themselves. When we try to reduce the vibration, we notice that if we try to hold 3 positions, the other vibrates stronger. So we use like more fingers and try to hold the other places, but then there are still more locations because the domain is continuous. So then the other locations start to vibrate more. So it wasn't really the right path. But with this modification, we can actually influence with much less energy the acoustic environment. And regarding the limits for the vibration amplitude, what we observed is that we could double the amplitude vibration of a specific frequency, maybe triple, but still the amplitude was not high enough to affect in any negative way the casings that we use for this purpose. So at least for this application that we considered, it wasn't an issue. So, the vibration were not really even noticed, were not perceived while we stood there. They were not also visible because the lowest frequencies, the highest amplitude can be even visible with bare eye. But in that case, we simply monitored and noticed it by our equipment, but it was not that high that it would be considered a problem. Perhaps there are such applications where we would need to provide noise reduction and also keep in mind the vibration. There could be such applications. But those that we consider at the moment, it wasn't an issue. And we could allow the vibration to be stronger. Thank you.
Okay, I think it's a good time to ask if there are any questions from our remote audience. We have a few people connected on Zoom, and I'm glad to see Professor Marek Pawelczyk connected as well.
Thank you very much. Hello.
Would you like to say something?
Thank you very much for inviting Professor Wrona to Technical University of Crete. I'm very glad that he could deliver a presentation because it is, I think, very much in line with the main subjects of EURECA-PRO, because we are talking about some savings in the use of materials and also energy use. Noise control problems are very severe for many applications and also for our households. So I believe that there will be some people interested in Technical University of Crete and perhaps in other universities of our alliance to contribute to this work. So we could be happy to invite them to our group, also to visit our university and also give a lecture, not only on this subject, because this is one of our initiatives to exchange scientists. And if any of scientists from Technical University of Crete are interested, we will be more than happy to invite them to SUT.
Okay, thank you very much. That sounds really good. Okay, any more questions? Okay, Professor Wrona, I think I have a challenge for you. The figures are nice, and we see that there is some reduction in the noise on different frequencies and so on. But I was wondering, do you have any audio examples where we can hear how the device operates, let's say, without any control, and how it operates after? Or because at the end of the day, our ears are the judges.
That's right. This subjective perception of the noise could be different. The figures are not everything. So I absolutely agree with this. I have more than 2 terabytes of recordings, so I will be happy to share. But yeah, at the moment, I don't have anything prepared on this laptop, but I would be happy to share such recordings, which shows this, how it feels, these 10 decibels, these 20 decibels. What is the difference? But in order to reproduce it, we need also a proper low frequency speakers. That's why usually I don't present these recordings on conferences, because the audio system in these conferences can often not really reproduce the lowest frequencies where we achieve our results. So the perception could be not appropriate enough. So I will be happy to share, but just mentioning that we need a proper loudspeakers in order to really feel the difference. Or we also can invite anyone interested to our laboratories and feel by themselves the vibrations, because that I believe would be the best experience. But if not, we can also share these recordings.
Okay, thank you very much. So we have another excuse to travel to Gliwice, I guess.
Definitely, we'll be happy to.
And not wait for the next review, maybe.
I think it will be an interesting experiment to hear very low frequency sounds, because as you said before, it is not usual for us to, our hearing, it's not sensitive to low frequencies. So it will be, let's say, a new experience if we have the ability to hear sounds of very low frequency. It seems to me that it will be something new.
Yeah, I believe that these lower frequencies we can perceive not only by our ears, but the whole body. So sometimes we can feel like a release that when we reduce these low frequencies, is not only hearing experience, but with whole body we can see relief that finally this noise is gone.
Yeah.
And it's easier to be in such environment when the noise is in different frequency bands. So the low frequency can be really annoying depending on individual people.
Okay, thank you very much again.
Thank you.
Okay, this is the last chance. I think we're done. Thank you very much once again.
Thank you so much.
And thanks to all of you for attending the talk.
Okay. Thank you for having
Have a
me
good
and
day.
your hospitality. Thank you.
Thank you.